Alright, hey gang. I've decided to stop putting my picture in the corner because it seems to be obscuring some of the words on there. And then, and so that you guys copy things down. Plus, I can make all kinds of strange faces while I'm doing this, and you'll never know, like right now. So anyways, we're doing section 1.8, which is combinations and functions and composite functions. I'm going to break it into two parts. First we're going to do combinations of functions, then we're going to do composite functions. And our goals are similar for both of them. We need to be able to perform arithmetic combinations of functions, and we need to be able to determine the domain of those combined functions. And we have to do the same thing, perform composite functions and determine the domain of composite functions as well. That'll be the second video. So what are arithmetic combinations? Functions can be combined to create an entirely new function through arithmetic means. In other words, they can be added, they can be subtracted, they can be multiplied, they can be divided. For example, and you may not think of it, but f of x equals x squared plus x minus 2 is really can really be considered the sum of two other functions, one of them being x squared and one of them being x minus 2. And if you were to take the graph of x squared and the graph of x minus 2 and add the two of them, it would give you this exact graph. So that's something that you probably had not thought of before, but that's what we're dealing with when you do arithmetic combinations of functions. What we're going to do though is we're not going to be starting off with this function here. We're going to be starting off with g of x and h of x and coming up with some type of arithmetic combination to give us a final function. Okay, so that's all we're going to be doing in this first video, is performing those arithmetic operations on functions and then simplifying them as need be. So what do these functions look like? What do these combinations look like? Well, you may see f plus g of x, which is the same thing as f of x plus g of x. Okay, typically we write it like this, but it means that. Let's see, what else? You could have f minus g of x, which is f of x minus g of x. You could have fg of x, which is just f of x times g of x. Or you could have a quotient. You could have f over g of x, which is just f of x divided by g of x. This should be familiar to all of you guys because I know you did this in Algebra 2 last year. So let's get to it. Let's say that we have two functions. F of x is equal to 3x plus 4. G of x equals x squared minus 2. I'm going to do four parts. First I'm going to take the sum, then the difference, then I'm going to multiply, then I'm going to divide. So I'll take those each one at a time. Did you see that? I just made another face at you guys. You couldn't see it. Okay, f of g plus, f plus g of x. So all we do is we take the f of x plus the g of x and simplify however we need to do it. X squared plus 3x plus 2 is your final answer. That's all there is to it. So we'll be doing about the same thing when we do f minus g of x. 3x plus 4 minus x squared minus 2 for a final answer of negative x squared plus 3x plus 6. Now this doesn't get mentioned very often, but typically we want our polynomials, which is what this is, to be written in descending order of the powers involved. So I always start with the highest power and go down from there. So 2, 1, and nothing there. So that should be what your simplified answer looks like. F times g of x, this is a little more difficult because we have two sets of parentheses to multiply. But heck, by now we're experts at foiling. We get something that looks like that, and it's not in correct polynomial form, so let's rearrange things slightly and get our final answer. That is that. F over g of x, 3x plus 4 over x squared minus 2. Is there anything I can do to simplify that anymore? No, not really. If the quotient can be simplified easily, then go ahead and do it. But typically that's good enough. There'll be some instances when your function ends up looking something like x plus 2 over the square root of 3 minus x. Okay? And the rule is we can't have a radical in the denominator. But for the sake of doing arithmetic combinations, this answer will suffice. You do not have to put it in simplest radical form. So keep that in mind when you have that situation. The domain of combinations. Well, first let's brush up on what domain actually is. There were only two primary concerns we had when it came to the domain. Can't have a 0 in the denominator because that's undefined. And we can't have a negative under an even root because that's imaginary. So those were our two restrictions. Well, the same rules apply here. The thing is, we have two different functions to be considering. In the case of f plus g, f minus g, and f times g, the domain has all of the restrictions that were present in each of the functions originally. Okay? That's for the plus, the minus, and the multiplication. So any restrictions that there were in f of x to begin with, or g of x to begin with, will still be present in your final domain. So let's say that you had a domain for f of x that included everything except x equals 4. And the g of x function happened to be everything greater than 0. That means that your final domain will include both of those characteristics. All real numbers greater than 0, but x cannot equal 4. So the combinations result in domains that we already know how to find. And it's fairly simple. Except for there's one more thing to consider if we have f over g of x. Remember, we cannot have a 0 in the denominator. So in addition to the restrictions from the very beginning of f of x and g of x, we have a final restriction, which is just that g of x cannot equal 0. So we still include the ones that were there to begin with, but we also have to consider that potential g of x equaling 0. Okay, so let's look at this example. These are the same f of x and g of x that we had earlier. Okay? And if you notice that the domain for each of those is all reals. There are no restrictions. There's no potential denominators of 0. There's no negative roots. So all real numbers. That means that the domain for f plus g is all reals. The domain for f minus g is all reals. The domain for f times g, on the other hand, is all reals. The only thing that we have to consider ourselves with is f over g. G of x cannot equal 0. So if you take the steps to figure out what that would be, g of x cannot equal 0. Well, you subtract 2 from both sides, take the square root, x cannot equal plus or minus square root of 2. Okay, hopefully that makes sense. I believe that is the end. Yes, it is. That's the end of this video.